have a simple procedure. You fall down, you break leg, you go to the doctor, you go to the hospital, get a simple plaster put in, and come back. If you don't have insurance, you will get a bill for $15,000 at least. $15,000. If you have insurance, this will be probably $20 or $40. Because that's how exaggerated the medical cost is in paper. Now, really, that's not the cost. But the insurance company ties up with the hospital, ties up with the medical company, ties up with the pharmaceutical company. They all tie up and jack up exponentially the cost and then say, look, the insurance is giving you 10,000% benefit. Right? So it's all artificial. So so the pharmaceutical companies, basically because of all this, they don't want you to be very healthy. If you're very healthy, what happens? You don't take any medicines, nothing, you're very healthy. Bad for them. If you're very unhealthy, the medical system is very expensive. Bad for them, because if I keep going to the doctor, if I have insurance, they can't deny anything, there's no limit. If I keep going to the doctor every day, if I keep going to the hospital every day, they spend money. So they don't want you to be unhealthy. They want you to be moderately unhealthy. Keep popping a pill every day. So that's why you have, again, have you heard of this cholesterol limited numbers that they came up with? So initially, we thought your cholesterol should be lower than 200. Then suddenly these American companies came, cholesterol cannot be higher than 160. What happened? 60% of the population of the world started taking cholesterol drug. Now, 17 years of patent of that cholesterol drug has expired for this company with the medicine called Lipitor. You would have heard of it. 17 years of patent has expired for it. Now, anybody can make that drug. What did the research come up with now? Cholesterol is not a problem. Eat up to 3 eggs a day, you're okay. Eggs are good for you. Eat up to 3 eggs a day. Eat the yellow. Until then they said, no yellow of the egg, only the white of the egg. Cholesterol. No, eat 3 yellows a day, you're okay. Right? They want it to be moderately unhealthy. So the problem is that you create structures that has to be always moderately unhealthy. In India, you take it to an extreme and say you have to be totally unhealthy in these structures, and then we patch it. Now, another example. I have been walking through the campus every morning because of nothing else to do early in the morning. Every building has vegetation on it. Every building, reinforced concrete building with a sunshade, has trees and plants growing on it. And then you complain about corrosion? Why? If you let the plant grow on it, you actually should have made it with mud, not with concrete. Right? So, first, design. Second, intended use. Third, upkeep and maintenance. Fourth, fifth, sixth, later on will come all the science behind what we have to do. So, in this environment, to control corrosion, if I give you a lecture on the porosity of concrete, the electrochemistry of steel, the passivating layer around steel, the ways in which electrons transfer from one place to the other, the way of expansion of steel to create stresses, I am wasting my time. Because none of these is ever getting to be a problem. Before any of these starts to act up, you have masked all of these by poor structural design practices, poor construction practices, poor upkeep and maintenance practices, and poor use practices. Before you teach a child how to multiply and do calculus and integration, you teach them 1, 2, 3, 4. Right? Before you teach them Shakespeare, you teach them how to read and write a simple sentence. That's what we need. We need good designs. We need climate appropriate designs. We need climate appropriate construction. I cannot go and lecture about how to create an ultra high strength concrete to a place that has only a convenience of a bowl and a few mixer and screws. I can't go and tell, here is how you make 100 megapascal concrete. All if you have is a measurement that can do 1.53 concrete, right? That has to change. And that is what you guys should put a lot of emphasis on what is the appropriate design. Now, have all the wonderful technologies in the world implemented in a building. You can have wonderful waterproofing, integral waterproofing admixtures thrown in. You can have the best epoxy to coat steel. You can have the best surface treatment primer on your concrete column surface. But if water drains through the concrete column with 400 millimeters or 4000 millimeters of rain that you get in Mangalore, you can calculate over the surface area of concrete with all these, what does 4000 millimeters of rain mean? I've given you all the equations for softivity and diffusion. You can sit down, make a simple calculation and tell me within 2 years how deep the water has penetrated. Right? So it is not about the science of it, it's about the policy and the procedure of it. And corrosion is an eminently controllable problem. When I say controllable, controllable for 50 years. Not controllable for life. Controllable for 50 years. Is that not enough? If your propagation time is 25-30 years, and by the time you get your rebar to be only about 70% of what you initially put in, where you think you should start changing it, if you get 50 years, is that not good enough? In the structure, in general structure. I told you about the nuclear reactive containment concrete that was supposed to last for 1000 years. Again, for those, you have to do all the things over and above. Here, to control corrosion, very, very simple. So, when my house in Kerala was being built, I was doing my, so at Kerala, like here, like your range, right? I was doing my civil engineering, and the engineer who was doing it was a very good friend of ours. So I had interest in concrete and at that time. So I told him I'll help you, I want to know what that is. So we still had the 1.53 concrete, whatever that is, right? They mix it in hand and do it. After all this, so this was 1992, so 26 years. We didn't have to apply waterproofing compound on our roof, and there is absolutely no leak inside. And I will tell you, we had at that time for low cost construction, so we were all big on Larry Baker, right? Hollow slab fillers. I even wrote 2 papers on filler slabs with mangrove pattern tiles, where you can space the reinforcement out and put in mangrove pattern tile. You've seen that? Where you put mangrove pattern tiles in the roof so that you cut, you don't plaster, you see roof from underneath. So this is Larry Baker's style. So we did that. So the reinforcement is much lower in my house compared to what we do now. Not a single leak, not a single point where I can see brown discoloration of corrosion. Who did it? The local guy. 1.53 concrete mixed with hand, it's working wonderfully well. So when somebody says it can't be done, I say no, absolutely it can be done. It has been done. Now also think about it. It has been done. We've had structures. There was a bridge in my hometown which was built. It was a very narrow bridge, so they had to demolish it to make the bridge wider. It was a narrow bridge, concrete bridge built in 1920s or so. It's a narrow bridge, and it's popping off and all of that. And they could not break the bridge with a jackhammer. They had to explode it. 1920 bridge. You can do it. People have done it. Right? So, a lot of times we create the problem to solve. Right? Corrosion, in a lot of these cases, is a problem that we have created. And sometimes the problem that we created, that is like the GD that comes out of the pot, and then GD becomes a problem. Right? We let the GD out, and now GD has become a problem. Lot of corrosion that we have, and I'll still go through details so that we can go through theory. But I just want to make sure that majority of concrete corrosion that we see here, and again when somebody comes and lectures about corrosion on electrochemistry and all that, it's all great. But until you control what you can control the best way, everything else is going to be a lip service. I mean, these are all academic, intellectual understanding. So somebody should say to the architect who designs all the buildings in NIT here, should tell them, sir, please don't give me Bangalore designs, give me a Mangalore design. Because these are all Bangalore designs. Bangalore doesn't get this much of rain, right? So probably the architect is coming from sitting in Bangalore, the CPWD architect or whoever is doing it is in Bangalore. He's taking designs that he does elsewhere. And you have this flat boxes where water falls right through the sides. A little bit of sunshade, little bit of extension to the ends, and a way with a few PVC pipes to take the water away, drain the ground towards different sides, take the water away, your foundation is safe, your roof is safe, your wall is safe, your structure is much easier. How much does it add to the initial cost? Maybe another 1%, 2% of the initial cost. If all these walls, if all these concrete and roofs get corroded, in 10 years, how much are you going to spend upkeeping them? 20, 30 years. Right? And the other important thing, whenever you see in any of the structures that you have, if they are concrete, they are not supposed to be growing trees. Concrete has a lot of minerals, but those are not minerals for trees. Okay? There are other places for trees. There should be other places for trees. Trees are not. So actually walk in the campus. Walk in the campus and see how many sunshade and wall sides. So you basically have your sewage pipes coming from the building. You see trees growing up, creepers growing up as if these are supports for them, creeping through. And when the creepers grow through, they have to attach themselves. They get the root. The roots are very powerful. They penetrate through these mortar because it's a very porous material, concrete. So they penetrate through. Roots they start holding them. They expand. Well, more water goes in, and then we say, how can this go wrong? We did it only 2 years ago. Right? So, 4 different things. Structural design, use, maintenance, and what was that coordinate told you? Inspection and maintenance. Right? This has to be there. If we get old, don't we go to a doctor to do yearly checkups? At least when you feel sick, wouldn't you go to a doctor? Well, doesn't matter what doctor you can do. You can be allopathy, homeopathy, Unani, whatever medicine you can go. But you still will consult some expert. You still will go to somebody who you believe, who you trust. Buildings also want that. They also want some kind of maintenance, some kind of upkeep, so that these issues don't happen. So now, assuming that all these are taken care of, let's talk about what happens. Again, this is not an India problem. Every country has the problem. US also has a lot of corrosion damage. The only difference is the structure that we speak there of having corrosion damage has been in life for 50 or 100 years. It's been there for 50 years, and we are talking about repairing and rehabilitating those structures because we cannot afford to tear them down. Think about the New York subway system. With all these trains going through 24/7, 365 without a stop, I cannot shut the New York subway down and tell people, yeah, find another mode of transportation, the city will die. You will have billions and billions and billions of dollars of loss in a single day. You can't afford to do that, right? So you do all this. And New York subway system has been there for 50 or 60 years. Now there is a lot of corrosion problem on the roof and stuff, but they never talk about it 10 years from the time it started. 50 years, reasonable, you can assume, and then they're trying to fix from stage to stage because you have roads around, water will seep and all that. But it is 50 years, 30 years, yes, but not in 4 or 5 years. So 1 billion per year is the economic impact of corrosion just with bridges and parking garages in the US. $1 billion, this is probably an old number, it might be even higher. Bridges and parking garages. Why bridges and parking garages in the US? Any idea? Bridges you put in the ice salt. Parking garages during snow time, all the roads and bridges will have all this salt. You drive through this salt, you come and park your car in the parking garage, and you go to your work. Parking garage is warmer than outside because it's enclosed. The ice and snow on the undercarriage of the car will start to melt and they will drop. So you will see localized pockets of corrosion on the floor slab, and they'll all do precast fixed slabs with nice anti-corrosion coverings, but still you will have that. So bridges and parking garages are prime candidates of corrosion. You have plenty of that. Simple idea: pristine concrete, you have crack widens, moisture goes through. When steel expands to how many times the initial volume? 6 to 7 times the initial volume. When something inside concrete wants to expand, it is exerting what stresses in concrete? Tensile stresses. Concrete has no tensile capacity, therefore it will crack. Cracking will continue until you have spalling, delamination, all of that, and reinforcing products will go on. Anode cathode story, all of you know that. It's a chicken and egg problem. Did cracking cause corrosion or corrosion cause cracking? We can always debate about that forever, but doesn't really help anybody to find out what caused the problem. You have to fix the problem. Both are issues. About 6 to 7 times the final volume, initial volume of iron through all the oxidation processes gets you about 6 to 7% volume. Corrosion will not occur if no water is available in concrete. Okay? Period. There is some water in concrete already. Can you avoid that water? We talked about core solution water not. But that water is available in these very small channels. That water, the cement is already there trying to use that water. That water is not really making you corrode the sample. Okay? But then you are getting water, massive water supply from outside, which is causing corrosion. Humidity, like water, like I said, is important. You need oxygen, you need the right kind of species. Now, so we talk about moisture going in. There are several ways in which moisture can go in. I talked about transport yesterday, right? There are several ways in which moisture can go in. It can be absorbed, it can be adsorbed, it can be, so combination of absorption and absorption that we talked about. It can diffuse, it can permeate, it can wick under the action of pressure, under the action of the pressure difference. All these ways in which you can go move. Now, when you talk about concrete corrosion, if you look at any, you guys have read papers on corrosion of concrete, right? What is the mechanism that everybody focuses on? Diffusion. You would have seen fixed second law being used as the standard expression of how moisture transports through concrete to have corrosion. Why diffusion? Why not permeation? I gave you the reason yesterday, if you remember. Permeation happens through the larger force. Permeation happens under gravity. Happens in the larger force. Sorption that we talked about. Sorption is also, we talked about the first 2-3 millimeters of concrete or cover depth of what happens. But after that, the transport, once you have a saturation, the transport is extremely slow. That slow process is diffusion. Diffusion is that slow process. Get that? Therefore, every theory of concrete corrosion talks about the mechanism of corrosion being, but that is not true if you have a really porous ugly concrete. Diffusion is a function of concentration gradients, right? So diffusion is very slow when you have a higher concentration at one side and a lower concentration at the other side, right? So you have diffusion. Now think about a structure that is, say, about a roof that is ponded with water. That has some standing water. There is no way for water to go. Because of sorption and all the other processes, the top little layer gets saturated fast. Right? Once that layer gets saturated fast, the concentration difference between this and that is going to be much lower because this is saturated, top also is saturated. Then the place that this entire head of water wants to go is below that. Right? So the next layer gets saturated quickly. Now it has a much higher head. The whole thing wants to go further. See how quickly the process goes? You get your steel in no time. You get how much cover do you give? 50 mm? 75 mm? You get your steel cover in no time. Especially when you have a porous concrete, when you don't have a very good concrete and when you have standing water. So think about when water slides through all these columns, you have a very high saturation. Yesterday I told you about relative humidity, right? Okay, inside also, the surface layers, I told you if you leave it in an environment like this with 45 or 50% RH, I told you it takes 25 years to dry out. It's that relative humidity already inside. And then you are subjecting it to a lot of relative humidity outside, your concentration gradients are becoming narrower, which means your process is going to go faster, your higher and higher concentrations, and therefore you can move faster and faster. Right? You have much higher concentrations, therefore you can move faster and faster. Get the idea? So that's what is happening in the idea of diffusion. If you want examples, perfume, mixing perfume and air, helium, helium balloon, all that. So I'll skip the math behind it, just show you the final concentration. So this is the concentration with respect to position. Think about moisture. Very high concentration of moisture at the top. Assuming that this is an example. Assuming that I have this much of moisture inside. Okay? So I have C naught is my concentration of water in my concrete. This is the trend that this line will take. Now what happens if I have very high concentration of water inside concrete because it's very porous? As this goes higher and higher, you see this line with position, this will go faster and faster to where it has to reach, which means you will get higher and higher concentrations at any position faster. See that? So this equation, the more you push this, this line gets to a deeper and deeper position faster and faster. Okay? So that's a simple reason why when you have higher porosity, you have faster corrosion. Let's take second law to solve. Corrosion is influenced by pore solution. So now we come to more academic sort of stuff. Having taken care of all the other factors, knowing that I have a good concrete, knowing that I have taken care of it well, knowing that the conditions are favorable not for corrosion to happen, then the transport is influenced by aspects of pore solution. Whether it's chlorides or moisture, it is influenced by aspects of pore solution. Now, most of the time, where does chlorides come from in India, where if you, in places where you don't put salt? Where does chlorides come from? Pore solutions, right? From areas like this, where your atmosphere is chloride laden because of ocean. So, this is a coastal problem. Is there chlorides in concrete in areas of India where there are no oceans? Can you get chlorides in concrete when you don't have ocean nearby? Yes. From where? From? You might have some adulterated sand with chloride. What happens then? What's the other thing? If you read from admixtures, from chloride containing admixtures. So normally you specify admixtures that doesn't contain chlorides, but there are some chlorides, especially if you use an accelerator, you may have chlorides in the accelerator. There's one more place where chlorides come from. Water. Cements are very good. Cements have no chlorides. Very, very negative. Water, right? You may have chlorides in water. So that also is a possibility. But let's ignore that. Let's just assume that this is a problem only in the coastal areas because the rest are all controlled. Right? I can't tell the ocean not to have chlorides. So that's a losing cause. But you can afford not to use chloride contaminated water. You can afford not to use chloride contaminated admixtures. You can afford not to use chloride contaminated sand. But let's assume it's coastal areas. In coastal areas, what happens is you have chlorides in the moisture in the atmosphere, and when there is very high humidity, when you have transport happening through, chlorides also will go in through the concrete. Now, I told you yesterday when we were talking about the rapid chloride permeability test, what are the two dominant negative ions in such concretes? Chlorides and hydroxides. Therefore, they are fighting with each other. Any material wants to be electroneutral because electroneutrality is a lower state of energy. Ionization, sodium chloride becoming Na plus and Cl minus, you have to supply energy. The moment you take the energy off, they'll go back to NaCl because that's a lower state of energy. Right? Na plus and Cl minus. So, when you have chloride ions and hydroxide ions, now you have imbalance because you have higher amount of negative charge. So they are trying to maintain a chloride to hydroxide ratio. I have certain amount of hydroxides already in my system, and then how much amount of chlorides can go in to create, also remember, chlorides have to go in towards the steel. Negative ions are going in a certain direction, right? hydroxyl ions, if there is a slight electric current and if that dictates where the direction is, hydroxides also want to go in that direction. Right? Have you heard of this idea called impulse current method of protecting concrete structures? Where you apply a current opposite to the direction of the front floor? Based on this principle. Because these ions want to go in one direction. So you want to manage the chloride to hydroxyl ratio 2.5 to 6, 2.5 times 2.5 to 6. So for every chloride, 2.5 to 6 times of hydroxides is typically the ratio beyond which you think, below which you think you will have corrosion problems. Viscosity of the pore solution. Remember I talked about swimming in honey and swimming in water? Chlorides will find it harder to swim in a very viscous pore solution. So if you increase the viscosity of the pore solution, admixtures are, there are some companies trying to create some admixtures, but like I said, it's become very expensive. But there could be, again, that's probably an area of research that somebody can do. Typically, if you can develop low-cost admixtures from some local, a lot of people are thinking about different plant extracts to put in concrete, right? You might find, and I don't know, I'm not a big fan of that anyway, but you might find some plant extracts that might be useful for such applications. Competing effects of alkalis, that also is, again, Na plus, K minus. When you have so much of sodium and potassium ions or positive ions, you need to have that much of negative ions to create balance, which means you need that much of chlorides to create balance. That electrolytes go through fast process. So effects of alkalis. Okay. Effects of corrosion of steel, you should have seen all these pictures. That is what I have for corrosion. General again. Let's start. If we can do, I can do 3 days of corrosion only. But just to give you a flavor for what the process is. Any questions? Any questions on sulfate attack? I can